Good morning and good evening, everyone. I'm Qingfeng Zhang, a researcher from Recon EIP. Today, I'm going to host the second TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon EIP to our valuable guest, Vikash and Tonghan. The full name of Recon EIP is Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as the research center for the MAX AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance AI fundamental technology and its real-world application. AIP encourages collaboration with various researchers and engineers in related fields. We would be grateful if you could visit us in our Nihonbashi office in Tokyo in the near future. Next, let me to introduce our valuable guest, Vikash Swag from Princeton University, and later Tonghan Wang from Tsinghua University and Harvard University. Vikash is a PhD candidate in electrical engineering at Princeton University. He is interested in research problems at the intersection of security, privacy, and machine learning. Some topics he had worked on are adversarial robust, supervised or self-supervised learning, adversarial robustness in compressed neural networks, self-supervised direct detection of outliers, robust open-world machine learning, and privacy leakage in large-scale deep learning. He is co-advised by Pritik Mittal and Mount Chang. Before joining Princeton, he completed his undergrad in E and ECE with minor in CS from IIT Kharagpur, India. He early had an amazing summer internship experience at Microsoft Research, Redmond. Before then, he spent a wonderful summer working with Heinz Koppel and TU Darmstadt. He has also received Qualcomm Innovation Fellowship in 2019. Let's sincerely welcome Vikash to give us his talk, A Generative Approach to Robust Machine Learning. Please, Vikash, please go see.
Yeah, thanks a lot. And I'm sorry for putting the all the details in the introduction. I should have shortened it.
No worry about it.
Yeah. So let me just set up everything. Okay, just to make sure, can everybody see the screen? And
yes, can see your screen and hear your voice.
Wonderful, wonderful. Okay, so hi everyone, I'm Vikas, and first of all, thanks for the wonderful introduction, and yeah, thanks for inviting me to this wonderful opportunity. I'll be presenting my recent line of work that focuses on taking a generative approach to robust machine learning. So I'll be considering two scenarios where machine learning systems often fail. First is the well-established direction of adversarial examples, where adversary adds a very small perturbation and makes a machine learning model fail against these seemingly benign looking images. For example, the dog image is classified as a goldfish in this case. The second more non-adversarial type of failure, where the system fails to recognize novel but hard instances at test time. For example, this might be image of a stop sign in common data sets that one trains in a self-driving system. But these are also valid stop signs that one can still encounter, and it's very unlikely that some of these images will be present. And even if they are, they will be present very rarely. So this is, in one way, it could be phrased as learning when data distribution is long tail. So I'll start with the threat of adversarial examples, and in the latter half of the talk, I'll be talking a bit more about learning with long tail data distributions. So with adversarial example, adversarial training is the go-to defense technique. The way it works is starting from data in a deep neural network. We first generate adversarial examples and then train the deep neural network on these adversarial examples. Very simple, but highly effective approach. Now, over time, and I mean last 5 years, there has been a tremendous interest in improving adversarial training. But as you can see, the progress has sort of saturated over time. And the question one can ask is, what is the bottleneck here? Is it the data, or is it that our training methodology in adversarial training is the reason of this bottleneck? Now, what I would like to argue that the data is the bottleneck. And to justify it, I would like to talk about sample complexity a bit. So sample complexity refers to how the generalization error on a data distribution reduces as we increase the number of training images. And in the context of adversarial training, actually, there is some preliminary evidence about how much helpful extra training data is. So on Cypher 10, we have 50,000 training images. But if we somehow able to get 500K, which is 10x more training data, then one can show that we can get up to 8% improvement in performance. Now, 8% improvement in robust accuracy is highly non-trivial, which is one way to show that adversarial training really embraces extra training data, or in a way, this is like a terrific insight into the sample complexity of adversarial training when we use common vision data sets with the extremely powerful deep neural network. Now, one can argue that the problem is actually solved. Why can't we just go ahead and collect extra real data? Now, if you follow that reasoning, it's very easy to argue that if extra training data was so easy to gather, then all our data sets would have millions and billions of images. Roughly what I'm saying is that there is a high cost associated with collecting real world data. And our approach is to circumvent this cost. So in particular, we argue to use synthetic data from generative models as a substitute of real data. And in particular, we make a case for using denoising diffusion probabilistic models, which I'll be referring to as DDP throughout the talk. Now, one might ask, why not use GANs? It's like a prominent class of generative models. And I'm pretty sure everybody in some context have seen the use of a GAN. So hold on to that question. I'll be taking a very deep dive into the generative models to use in just after 4 to 5 slides. But roughly, what we want from a generative model is to closely approximate real data distribution. And as long as it does that, we can argue that the synthetic images generated by the generative model will be very similar to real images. For example, here on the left, we have real images from ImageNet dataset. And on the right are some synthetic images from DDPM model on the ImageNet dataset itself. One more thing I want to highlight here is that the argument or the framework is not limited to generative models. So in essence, what we want is extra training data from a distribution that is a close approximation of real data distribution. So to make the arguments not being limited to the distribution learned by a generative model, and to keep it more general, I'll be using the notion proxy distribution. as it covers generative models plus any other model or any other technique that has learned an approximate distribution. So this is more of the notion, like what does approximate distribution mean? If you see it at some point in the slides, though, like right now, though the notion of approximate distribution is general, like right now, I'll be using it interchangeably as with generative models. So it's again. So I was just looking into the chat. Yeah, please feel free to ask any question throughout the slides or throughout the talk. So it's very straightforward to incorporate proxy distributions and robust training. And as I said, when I'm using proxy distribution, you can interpret it as using generative models and robust training. So we start with the training data set. We train a generative model, which could be a GAN or which could be a diffusion-based model. And then we generate synthetic data from it. Now, there is some caveats if the generative model is conditioned or conditional or unconditional, which means does it just generate images or does it generate both images and labels? And depending on answer to that, you train some pseudo networks to get some pseudo labels for the synthetic data. But in reality, what we observe that it's really straightforward to train conditional generative models too. So one can easily circumvent this step by forcing the generative model itself to do both images and labels. Now, once we have trained the generative model, we can sample synthetic data from it. Now, unique quality of generative models is that they are a source of potentially unbounded amount of data. So even though we had only a limited number of training images, we can combine them a very large set of synthetic images and then train a classifier jointly on both data sets. And that's why the abbreviation for that doing robust training with both real and proxy distributions. Now, how much synthetic data helps, or how much successful port is in the real world setting? So we consider most commonly used data sets in computer vision and find that across all of them, using synthetic data helps. And permanently on CIFAR-10, we get an improvement of 7.5%. And if you remember earlier, I mentioned that using extra real world data gave an improvement of almost 8. So you can see just using synthetic data itself is a good substitute of real data across most data sets. Now, I would also highlight one limitation. If you see on ImageNet, the improvement is relatively small. And this is sort of an insight into generative model also, is that right now the state of the art can easily approximate, easily model data sets like CIFAR-10, CIFAR-100, because they are relatively simple. ImageNet being like the hallmark of computer vision and being like how complex it is 1,000 classes. Each class have real world images and they involve scenes, they involve complex objects. So this is like a very tough to model distribution, which is why the synthetic data generated on ImageNet often sometimes it's not being super realistic. Sometimes the model have trouble achieving a high coverage. But on other commonly used data sets, as you can see, the improvements are very high. Across, as I said, synthetic data, generative models are a source of potentially unbounded number of training images. So across each of these data sets, we at least sampled 1 million of synthetic images, and for CIFAR-10, we even V1 went up to sampling 10 million images. As it's intuitive to see, more training data always helps. So since the generative model allowed it, we try to maximize the number of training images we could sample and train on. As I was saying earlier, the improvement we got from using synthetic data is very significant, and it is a more quantitative conversion. So we deliberately used very simple techniques in our paper. So we started with PhD-based adversarial training. That was one of the earliest approaches, and combined it with synthetic data, with an additional insight that was that one should use strong regularization. So as you can see, using strong regularization boosts the performance. And on top of that, if you add synthetic data, it gives another very large boost. And the gain actually surpasses many papers, and most of these are algorithmic innovations. So another way to look at the benefit of synthetic data is that it is more than equivalent to many algorithmic innovations that are being made in the space. But also, it is actually not limited to just PhD-based adversarial training. One can take any of these approaches and combine them with synthetic data. Now, this is a seemingly simple approach, but I would like to argue that it requires understanding of why does synthetic data helps. Which generative models should we choose? For example, by DDPM, but not GANs. And are all synthetic images equally helpful? So I'll be delving into each of these three questions one by one. So why does synthetic data helps? Now, one can simply, just a bit of notation first. So D and D tilde are referring to real and synthetic data distribution. Synthetic data I also refer to as proxy distribution. And now let's assume that we start with a set of training samples from the proxy distributions. That is S hat. Now one can show that by training on these synthetic or fake images, the robustness achieved on real data distribution is, of course, how much robustness we get on the training data itself. That's always there. Plus, there is always a generalization gap from data, from a limited amount of training data to a distribution. That's also there. But now there's also a distribution shift penalty. So the larger so the way to interpret this distribution shift penalty is that if D and D tilde are very different from each other, then we are going to pay a very high cost in generalization or generalization of robustness from D to D tilde. Now we can actually quantify this cost, or we can actually give a bound on that. What if I say train a model on the distribution on the proxy distribution and measure its performance on the real data distribution? So one can actually prove that the difference or this generalization gap is actually upper bounded by the condition, by the Wasserstein distance between the two distributions. So this sort of established this intuition that if my proxy distribution is close to real data distribution, then I would get large benefit from using the fake images from the proxy distribution. And also it motivates one to find a proxy distribution that is as close as it can be an approximation of real data distribution. Now that brings me to the second question, which is which generative models should one choose? As I was saying earlier, we should try to best approximate the real data distribution. Now the question is, which model does that? Which model is the best approximation? And before diving into that, I want to pose a question to the audience. So what I have here on the upper left is real images from the scikit-learn dataset. Here, if you can see my cursor on the upper right, we have samples from the diffusion model. On the lower left, we have samples from StyleGAN, which is the state-of-the-art GAN approach on scikit-learn. And on the bottom right, we have also StyleGAN. Now, the question I'm posing is, can one tell by just looking at these images that which one of DDPM, StyleGAN, or versus StyleGAN, like which one of these three is going to be most helpful? Or which one of these three set of fake images are going to be most helpful if I combine them with real data? And frankly, every time I ask this question, if I haven't presented well ahead of time that diffusion model works well, then it's very hard by just looking at these images to say which one of these three fake images or fake synthetic or data distribution or proxy distribution are most close to the real data distribution. Because all of them captures image semantic, like the dogs, frog, horse, all images, they do look like the real images. And though these fake images have their own artifacts, they are very hard to spot. So what I'm trying to hint towards here is that it's very hard to just look at individual samples and say that which one of these synthetic data distribution will help the most. And what we need is a distribution level comparison. Okay. So in particular, what we want to measure is how much real is a fake data, is a fake data set, or how much close to real data distribution is a proxy distribution. Now, we first measure it quantitatively. So we take 7 different proxy distributions or equivalent, or 7 different generative models. The first is DDPM, which is a diffusion model, and rest of them are GANs. What we do is train on 1 million synthetic images from each of these models and test the performance on the real test images. Now, we find that the robust accuracy, we just train on 50,000 scikit-learn training images, we get 48.7 on test. On DDPM, if we train on 1 million, we get 53.1 test accuracy on real data. Now, the number is higher because the training images from DDPM are 1 million, not 50,000. So that's why you see that training on fake data is actually doing better than real data. But the main point I want to highlight here is the benefit we get from different generative models. Models like DDPM generalize very well on the real set, but models like big GANs don't. So this is a quantitative validation of why GANs actually do not generalize well to real data distribution. And I mean that if we sample images from GANs, the relative benefit on real data is not that large. And I'll be, in the next few slides, we'll be explaining why that is the case. But what I want you to remember is the ranking from this table is which models does the best and which model does the worst. And of course, like this is not the first time one has asked this question. In generative modeling literature, there are common metrics like FID, inception score, that are designed to measure how much real is the fake data. And we find that though these metrics have their own unique advantage, for the task we care about, which is how much is the robust accuracy we get, these metrics are not actually predictive of it. So they actually say that, so the FID score actually ranks StyleGAN above diffusion models. And as you can see that the style gain benefit is not as large. There is a difference of more than 8%. So this limitation of existing metrics actually compelled us to indeed look deeper into this phenomena and come up with a better metric. And there's like slight humor in sort of like the approach we took, is that we wanted to fix the issue of adversarial attacks, but we actually ended up using adversarial attacks as a tool to come up with a better metric. So the principle of the approach we took is that two distributions are close to each other if we have a hard time doing a binary classification between them. So if I have, say, 1 million fake images and 1 million real images, then if I can successfully draw a decision boundary between them, that could be a proxy of saying whether these distributions are close or far away from each other. But there is a subtle challenge we ran into here, which was that deep neural networks are highly expressive. Even just a few layer neural networks are, we found them to be powerful enough to distinguish between fake and real data. And sort of like you can see the intuition here, that if I start with real images, the blue dots, and if I take two proxy distributions, one very close and one very far away from real data. And the issue is that since neural networks are powerful, they can draw decision boundary even from these like super closed data distribution, because they are capable of drawing complex decision boundary. So that's why this original approach of doing binary classification failed in giving us insightful metric. But as we know that we can use this very simple technique of epsilon law. And what it simply means is that rather than doing a benign classification, we do a robust classification, which means that around every sample, we draw a LP ball. And now the objective is not to draw a decision boundary between between the samples, but draw a decision boundary that does not intersect these LP balls. And as you can see, now the task is easier between real and fake data that's far away from each other. But now it's close to impossible for fake data that's very close to real data. And one can actually interpolate on the size of the epsilon balls, like starting from 0, which is like no epsilon ball around samples, and slowly increase it. And as we increase the size of epsilon balls, we train a binary classifier on it and measure its success. So the hypothesis is again very simple. If fake data or if synthetic data is very close to real data, the binary classifier is going to have a very hard time classifying it, even with very small epsilon balls. And that actually shows us very interesting insight that if we consider DDPM or the diffusion model samples, even with a very small perturbation, like very small epsilon, it's close to impossible to classify real from fake data. Style gain, which is the second best approach, also shows the same phenomena, but at a much larger epsilon ball, which means that style gain images are relatively farther away. And rest of the synthetic data distribution, again, like it doesn't get much harder for them. So one can very easily come up with a metric of how hard it becomes as we increase the size of perturbation budget, which is the area under this curve. So we refer to the quantity as R, which is area under the robust discrimination versus epsilon curve. So the smaller the area under this curve, the quickly it's falling from 1 to 0.5. And this area or this metric R, as we show, is a very accurate predictor of which generative model is going to be most helpful and which one is going to be least helpful. The third question we are interested in is are all synthetic images equally helpful? Now, in interest of time, I'm not going much digging deeper into this, but the notion of the hypothesis here was again very simple, that we want to pick synthetic images that are closest to real data distribution. And on the notion of proximity, again, we use the previous metric arc that we developed to judge the proximity for fake data. And we show that, again, the gains are not very high, but one can obtain relatively some improvement by doing this adaptive sampling, or by sampling synthetic images based on proximity rather than uniformly sampling them at random. So the key takeaway from this line of work was that proxy distributions significantly boost performance of adversarial training. Our full paper is already there on archive and to be appear in ICLR 2022. And I think the camera-ready version will also be shown up on the website, and you can find all the new results that might not be there in the current draft. So I'll switch gears, and in interest of time, I'll be quick about this second research direction, or the second challenge, which is that we want to come up with a way to sample novel but rare images in our data distribution. So I want to again recap what I presented on the first slide, is that real data distribution is often long tail, which means that we have a very large number of samples that are from high density regions. For example, for this monarch butterfly, these real images from imaginary distribution, you will see many of them where it's like the image is taken like in good lighting conditions, object is centered, well captured. But then there is a very small fraction of images that are novel, rare, much harder to recognize. And as you can see here, in most of them, even for a human, it's very hard to identify that it's a monarch butterfly image. So the takeaway here was that low density data is relatively present in very small quantity. And that's why it's called low density in first place also. And even our modern data set has do actually suffer from this long-tailed nature of data distribution. So to bring more evidence, I want to tell a short story about Tesla and stop signs. And the credit goes to Andre Carpenti for sharing this in his talks. So commonly the stop sign images, these are the stop sign images one might see in common scenarios or in like high density regions of the data distribution. But what he argued is that in real world, even detecting a stop sign is extremely challenging, just simply because the novel variations one sees in the real setting. So for example, the stop sign in some cases is occluded, like it's behind a pole, behind a tree, and in some setting it's like literally almost on the ground. And one of the most funny ones was that somebody was holding the stop sign inverted. So these are the rare cases which one doesn't often see, or these are like these low density instances that are missing, or that are present in very small quantities in our modern data set. And what the focus of my work is precisely on how can we gather more low density data in a more automated and in a more sustainable fashion. Of course, like Tesla being Tesla, like they have a fleet of more than 1 million vehicles. So they actually developed manual triggers to actually source these hard instances or these rare instances. But since that luxury is not available, like what if you're on Tesla? I think the next best approach is that we source data from real world using, say, using search engines. And since that's the way most data sets are collected in real world, and use AMT to filter out the images. But then again, it's challenging since collecting a data set often is a year long, if not year long, it takes months to do it. And then one have to do the same process for every single data set. So there's high cost associated, and it's a repetitive process and needed to be done every single time for every single task. And the question I'm asking is, can we develop a more automated process? And in particular, as you might have guessed, can we use generative models to come up with some solution for this very challenging problem? So our approach here is that given a data distribution, first we learn an approximation of the data distribution using generative models, again using diffusion-based models. And then we develop novel sampling techniques that can sample specifically from the tail of this distribution. So the sampling process in diffusion model is a bit tricky. So instead of a single shot sampling, as it is in GANs, diffusion model involve a repetitive sampling. So rather than, like, the intuition here is actually quite simple, that you start from a noisy image and you iteratively denoise it. And the iteration often it's like 200 to 1,000 iterations. And what we did was we modified the sampling process to guide it to low density regions, or guide it to the tail of the data distribution while maintaining fidelity. And this is like a two-step process. Again, I think I don't have time to go deep into details here, but what we show that if one just guided the sampling process to low density region, you risk losing fidelity. So for example, starting from this, without any guidance, the generative model would have generated this nice looking image of the butterfly. But if we just force it to sample a low density image, it generates something that's not photorealistic. Now, of course, that image belongs to low density region. It's rare, but it's not photorealistic anymore. So then we need another guidance term that makes sure that the data is low density, but at the same time is a real looking image, or it have high fidelity. And we find that this approach is extremely successful. Now, I want to give credit to diffusion models also when I say that this approach is successful, is that any sampling technique cannot generate any sampling technique cannot generate something that the model has not learned. So it's first up to the model to learn data distribution near the tail also. Then it's up to the sampling technique, which is our contribution here, to actually guide or to actually probe those regions of the data distribution. And we find that that, of course, like again, like we didn't try this approach with the big GANs, as you can see that that GANs, when it comes to ImageNet data set, have a very hard time to generalize in first place. So this is like a non-problem of mode collapse. But diffusion model, which is like the baseline setting, if we sample uniformly at random, we get very diverse set of images. But if one uses our sampling technique, one can really generate very rarely occurring samples. For example, I'll come to the question in a while: is that are these samples truly rare or not? Before that, a few more examples from ImageNet. The bottom row is the baseline setting, which is we sample uniformly at random from the diffusion model. The top row is the sampling using our techniques, which is we sample novel and rare images from low density. And as you can see, for example, for the water tower, the rare images, as one might expect, they are in poor weather conditions, lighting, most of them are at night, and there are no camera angles involved. For tiger beetle, again, it's the same thing. Like there are, so out of 1,000 classes on ImageNet, there are like only a few that have a person holding the tiger beetle. So that's why one might see that actually the definition or the expectation of a rare image is actually somebody holding a tiger beetle. So this is like sort of like a mini proof of concept that the network is actually probing the low density images. A bit like again, a qualitative observation, which was that we observed that for these lantern images, our sampling technique was able to generate purple jack-o'-lantern images. So I actually went through all 1,000 images in the ImageNet training set, and I found there were only 2 jack-o'-lanterns which were actually purple in color, and these 2 nowhere looks close to them. So what I want to highlight here is that the model is not actually simply memorizing low density data, as one might expect, since it's only just 2 images to learn from. But these diffusion models are actually quite powerful, that even in the low density regions, they are able to successfully generalize. And our sampling technique is taking advantage of it by probing these regions. The second question is it truly hard instances? And again, the answer there is affirmative. We quantitatively analyze it by measuring the distance to nearest neighbors to real data. And as one can see that, the baseline sampling, which is sample uniformly at random from BDPM, is very similar to real data. That's like a proof of concept that diffusion models are really good at approximating real data distribution. And what our sampling technique, as we designed it to push or like sample from these low density regions, or sample from regions that are far away from high density region, we see that the average distance that our synthetic image will be close to a real image is much higher. More qualitative comparison is here, where we take a synthetic image, which is like the first column, and look at the nearest neighbor in the real data. And then we look at how do these which class the nearest neighbor belongs to. And this is like very surprising. For example, this hourglass image, you find that the nearest neighbor in the feature space over ASMA 50 are actually of different classes. So this is again a proof of concept that this image is actually rare or low density, that the feature extractor or the common deep neural network think that this is like a plate rack. or a plain glass or a salt shaker. It's able to not recognize it. And similarly, from like many other cases that we have in the paper, and even more quantitative analysis we do to show that the data is that the network is truly generating harder instances and that it is not merely memorizing these images. Again, the key takeaway is that diffusion models can generate novel and rare images from the data distribution. The paper is under review, but it will be soon in a matter of week or two. It will be there on archive. Thank you for listening, and I'll be happy to answer any question.
Yes, in the chat box, we have two questions. Maybe you can explain, answer them in reverse way. One question is, can you explain the proposed sampling techniques once again? Is it only applicable to DDPM? Hi, Vikash, I cannot hear you. Your voice is muted.
Yes, sorry, I will.
Sure.
Yeah, my apologies, as I only explained the intuition behind the technique. So what we are doing here is that, so as you can see here, at every, the diffusion model is simply a deep neural network that takes a noise image and maps it to or denoises it. So one in a sense can say that it's a denoiser, though it's a bit more sophisticated than that. But it's kind of like generates this step delta that from xt, if you add this additional signal delta, you get a denoise image. Now, when I say we are guiding the sampling process, I'm generating another additional signal, and that is coming from a classifier, a pre-trained classifier. And I'm adding the delta given by diffusion model and the guidance delta I get from the classifier. Now, what is the additional classifier? Like, how is it the additional classifier is sort of like guiding the sampling? And again, that's also very simple, is that what we are using is the gradient of the cross entropy loss, or it could be equivalently gradient of say Mahalanobis distance, or equivalently log likelihood in the feature space. So it could be any one of those, but it's simply saying is that given image xt, what should be the additional gradient or what should be the additional term I should add in xt, such that this image will be classified as a butterfly with lower probability or with less likelihood. So when I say we are guiding sampling process to low density region, we are sort of, our hypothesis is that the data in low density region is classified with relatively small probabilities. So if we force the sampling process to give us images that are classified with smaller probability, we hopefully will be able to sample low density region. And this is why we ran into this caveat that it's the network sort of like you can literally clear out the whole image, or you can just generate like a white background, and even that's classified with a low probability. So we needed an additional guidance term, which again is a classifier, but this classifier is a binary discriminator, as we trained in the previous project, which is a real saying. It's like the discriminator used in GANs, equivalently the same discriminator, but this is forcing the generated image to stay close to the real data distribution. So that's why it forces the sampling term not to drift away from the data distribution and go to this red dot, but stay on the data on the data manifold and generate something that's on manifold and low density. Did that answer the question sufficiently?
I'm thinking kind of you modifying the noise added, or you modifying the diffusion model. The diffusion model is basically indirectly call the model like a neural network and adding the Gaussian noise to get the final synthetic image. You modifying the noise added to the diffusion, or you modifying the diffusion model directly to the
so the model is pre-trained. So the sampling stage assumes that the model is pre-trained, and it innovates into how do we extract, or like any sampling technique innovation. So yeah, it innovates into how do we move from, let's say, from XT. The diffusion model is fixed. We aren't touching the diffusion model. So the diffusion model gives its own delta that one adds in XT. And we are bringing additional, like we are adding these external signals in the sampling process. So the diffusion model is not being modified.
Into the noise, we change the Gaussian noise to additional kind of signals. Right.
Yeah, if we say that, so the diffusion model, it's sampling less than noise from this p theta. So then we can say that we modify that additional noise, or like additional denoising signal given by the diffusion model, and add these additional guidance terms into it.
Thank you. Yeah, we also have more questions.
Can
you read it?
I can
sure.
Go through one.
Yes.
Sorry, what is the symbol H? So I guess this was from earlier slides. So H, we are just referring to a classifier. So this is like a standard notation, like a hypothesis class, which essentially translates to a classifier. So I hope it clears the confusion. Otherwise, I can go to the slides if you need to. Yeah, I guess it will. The other question, it seems that we never introduced new knowledge into adversarial training, since we generate extra data only based on original data set. Yes, precisely. That was the motivation from start, that we should not have any additional dependence on extra real world data, since it's not easy to curate it. Why can't the current classifier take full advantage of the original data set? Or does any implicit knowledge from the diffusion model helps adversarial training? I think this is an excellent question. And I still believe that we haven't fully answered this one in the paper. Like frankly speaking, it's like super hard to pinpoint why current classifiers couldn't take advantage of the original data set. And the analogy I generally give is that you can think of diffusion model giving a helping hand to the classifier. So something like mix-up. A mix-up is a technique where we interpolate, it's a data augmentation technique that we take two images X1 and X2, we interpolate between them and train on these interpolated images. And in a way, this interpolation sort of like makes the classifier learns to correctly classify these novel samples. So the analogy I generally try to present is that the generative model is doing this novel data augmentation for the classifier. That of course it's only using the 50,000 training images, but it's interpolating between those 50,000 images in the data manifold and coming up with these novel samples, which as we know, even with modern classifier, data augmentation is something that we give to the classifier. So we tell the classifier that this is XYZ is the data augmentation technique, better the data augmentation technique, better the performance of the classifier. So one can think of GANs being one of the best data augmentation techniques that one can use. Of course, it's certainly more than that, but I hope that one analogy kind of like shows why current classifiers couldn't by themselves get the same gain that we got by using extra fake data. Yeah, I think we already covered the proposed sampling technique. Is it only applicable to DDPM? Yes, this technique is only applicable to DDPM. And I would say the whole reason to develop this technique was because this iterative sampling process in DDPM. If it was a GAN, I think there are already approaches, because in GAN, we can do an end-to-end propagation. Which is not feasible because, as I said, there are 1,000 optimization steps just to generate one image in a diffusion model. But if it was again, there is no need to develop any complicated sampling technique that sort of like we did. One can just do end-to-end back propagation and very easily solve this task. In the analysis slide of 3 terms affecting the robustness, by minimizing the last term won't increase the other terms. These 3 terms should be independent for us to be confident to minimize each term separately. Yeah, that's a good question. Let me think for a moment about this. So the first 2 terms are actually not independent of each other. So this is like the classical generalization gap, that you train on one data set, and since data set is only an approximation of the data distribution, there always remains, or like there remains a generalization gap. Yeah, I don't know like precisely what does it mean for the third term to be independent of the first 2, because again, like one can choose D and D prime as the same distribution. Yeah, but like my take still will be that sorry, I missed that. Okay. My take still will be that it's very likely that if, say, on a proxy distribution, let's just say you increase the data set size, which means that you are tweaking the first 2 terms, that you increase the robustness on the training data set itself, you reduce the generalization gap. And I guess it's very hard, like it's like if the synthetic data or the proxy distribution is totally far away or totally unrelated to real data distribution, it's hard to say whether it will boost performance or not. But the motivation was to say that there remains an additional penalty, or there remains this gap. But will it increase or will it decrease? I think that depends on a case-to-case basis. Though I should say that those 3 terms, like mathematically, you can say that they are just restructuring. So that's like basic algebra, and altogether they are actually like equal to the robustness on the real data distribution. So there are like no surprises there. It's just a rearrangement. So when you guide sampling process towards the tail, if instead Gaussian noise, if you use Gaussian distribution, which is more likely in real world complex environment, it will push similarly. Have you seen this your work? Any comments? So I think your question connects to this ongoing research direction, which is a bit orthogonal to our work, which is that why we are modeling, or why we are making this prior that each step in the diffusion process is modeled using a Gaussian distribution. And by all means, one does not have to make this assumption. There's already a paper that uses gamma distribution to model the diffusion process. And of course, you can go ahead and use a cautious distribution. Again, the trade-off I want to highlight is that, yes, by using a complex distribution, you're making each step of the diffusion process more powerful. But the trade-off is first from that one should be able to come up with sort of like a very simple training objective to train the model, which again, it's a mean square error when one chooses a Gaussian. I'm not sure what is the case for Cauchy. And each step of the diffusion process should not be super complicated. In the sense, it should be still remain easy enough for a generative model to tractably solve. But indeed, yes, it is certainly a very active research direction. And yes, having a more powerful or having a more realistic, so in a way, a data-informed distribution is going to be more helpful in the sampling process. For example, there's ICLR 22 oral paper that actually uses a GAN to model the distribution of each sampling, distribution of each step in the diffusion process. So yeah, there's a lot of interesting work going in that space. I hope I didn't go too much over time, but yeah,
Thank you. Yeah, your talk is very interesting, attracting many interesting questions. Thank you very much. Hopefully, in the near future, you will visit us in Yohobashi office in Tokyo. We very appreciate for your excellent talk today.
Thank you. Yeah, okay. Yeah, looking forward to it.
Yeah. Okay. All right. Next, I'm going to introduce our second guest, Tonghan Wang. Tonghan is currently working with Professor Chongjie Zhang at the Institute of Interdisciplinary Information Science, Tsinghua University, headed by Professor Andrew Yao. He will join the Econ CS group at Harvard University and working with Professor David Parks. His primary research goal is to develop innovative models and methods to enable effective multi-agent collaboration, allowing a group of individuals to explore, communicate, and accomplish tasks of higher complexity. His research interests include multi-agent learning, reinforcement learning, and reasoning under uncertainty. Let's hugely welcome Tonghan to give us his talk, Role-Based Deep Collaborative Reinforcement Learning. Hi, Tonghan.
Hi.
You can proceed.
Thanks for your introduction.
Yeah.
Hello all. Today my topic is about role-based deep cooperative reinforcement learning. This topic is in the field of multi-agent reinforcement learning. And our goal is just want to introduce the concept of role into the system of multi-agent reinforcement learning. So since I'm not very familiar with the background of the audience, I will just start with some basics of reinforcement learning. So if all of you are very familiar with this part, you can just interrupt me and I can skip this part. So reinforcement learning is one of the major paradigms of machine learning, and a little bit different from supervised learning or unsupervised learning. It involves an agent who is interacting with the environment. And the target of this agent is to just learn some policy to solve a task from its past experiments or experience. So the agent is interacting with the environment and it is receiving some states and rewards from the environment. And it will take some actions to change the environment. And its aim is to get more reward from the task. And the basic idea of reinforcement learning is that the agent should take some more rewarding actions more frequently, so that in expectation, it will get more rewards and finally solve the task. So in the area of deep reinforcement, deep learning, the agent is typically deep neural networks consisting of several convolutional layers and fully connected layers. So multi-agent reinforcement learning is a branch of reinforcement learning. When we say reinforcement learning, we are seeing that one agent is interacting with the environment and learn some policies. But multi-agent reinforcement learning involves more than one agent. And it is kind of learning some cooperative policies to solve a team task. For example, a robot team, we let a team of robots to play the soccer ball. And there are many applications of multi-agent reinforcement learning in real world. For example, multi-agent assembly. In recent years, multi-agent reinforcement learning has witnessed many prominent progress. For example, it has been used to study the emergence of tours, and it has also been used to solve StarCraft 2 micromanagement tasks. And the central policy of multi-agent reinforcement learning is that we want to learn some control policies for a team of agents. And there are several major paradigms for learning such a control policy. The first one is joint action learning, which means that we can treat all the agents as a meta agent. The advantage is that we can use the algorithms for single agent reinforcement learning to help the team of multi-agent to learn the policy. And we don't need to design new algorithms for multi-agent teams. But this disadvantage of this paradigm is that we need some global states. This global state is always unavailable when executing. For example, sometimes the communication channel is limited, so that we cannot transmit all the local observations of the agents to other agents. So this will limit the application of this joint action learning paradigm. And another paradigm is called independent learning, and it can solve the disadvantage of joint action learning. It just treats an agent as decentralized learner, and the policies are decentralized, and it is only based on local observations. So the advantage is that it doesn't need global states, but it also has some disadvantages. For example, it suffers from the problem of learning non-similarity, which means that since the agents are independent from the perspective of an ego agent, the other agents are also learning and interacting, so its environment is always changing. And a very basic assumption of reinforcement learning is that the environment should be static. But when in multi-agent reinforcement learning, since other agents are learning and changing their policy, the environment is also changing. So the static, so the environment is not static, and this basic assumption is violated. And recently, a very popular paradigm is called centralized training with decentralized execution. And this paradigm holds a promise to combine the best of the aforementioned two paradigms. In this paradigm, the agents are decentralized, but they are trained in a centralized way, so that they can share their parameters and their gradients. And in this way, the learning non-similarity problem is just avoided. However, the policies are still decentralized, and it only conditions on some local informations, such as local action and local observations, so that the agent can execute in a decentralized way, and it doesn't need any global states. And the paradigm of centralized training with decentralized execution has adopted by many recent works, and it has been used to solve problems like multi-agent exploration, communication, and policy learning. And actually, many aforementioned progresses in multi-agent reinforcement learning is achieved by this paradigm. But the centralized training and decentralized execution paradigm has a very significant drawback. That is, the action observation space is really large. The agents just learn in this space. They want to map the action observation input to some actions. So when agents are searching in such a large space, which grows exponentially with the number of agents, it just cannot solve the problem efficiently. Sample efficiency is always a concern of reinforcement learning. When you have many agents, you need more samples. And actually, when this space is exponentially large, you also need, for example, 2 million samples to solve a very simple task. So these drawbacks lead to the fact that the paradigm of centralized training and decentralized execution is not suitable for complex tasks. So how can we solve this problem? We can get some hints from our humans or some insects. When facing a very complex task, we humans never want to solve it directly. Instead of that, we want to just group our humans into different subgroups so that we can take different subtasks. And actually, this is a concept of role, right? It is a kind of labor division. You just have different people to have different goals, and you together can solve the task. This phenomenon can be observed in daily lives and some insects like ants. So we just propose the concept of role-based reinforcement learning. Actually, it is not a very novel idea, but previous work mainly based on some prior knowledge. For example, in robot soccer teams, it just defines some goals like goalkeepers and forward and something like that, so that it can just decompose the task and let different robots to focus on different subtasks. It decomposes the task, but it is based on some prior knowledge, so that you cannot easily transfer the role-based knowledge to a new task. So it has many advantages. But in this, in our work, we want the agent to learn from scratch. They can just discover some roles and some role policies. They can just learn to decompose the tasks from scratch. They learn this from scratch. So our question is, how can we just effectively find a set of roles that can decompose a task? To solve this problem, we just propose a method called ROMA. The basic idea is that agents start from some random exploration. And during this process, it will just find some useful behavior patterns. And we want to find a set of roles which can represent this set of behavior patterns. And in this space of roles, we can use some techniques to encourage role clustering. And when we map the roles back to the behavior space, the agent will just take on some differentiated behaviors. So that in this way, we can just achieve the encouragement of behavior differentiation by introducing the concept of roles. So two very basic problems here is, how can we just find a set of roles to represent the patterns, which we call the identifiability of the roles. And the second problem is that how can we just introduce encourage the clustering of roles, and we call this process a specialization of these roles. To solve these problems, we take such a neural network architecture. First, we have some local observations. The local observations is the sensor input of the agent. For example, video or some vector inputs in the game of Go. And this observation will be input into a row encoder. The output of this row encoder is a row distribution, and we can just sample a row from this distribution and input it into a row decoder. The row decoder will generate the policies, the parameters of the policies from this row. So the row encoder is in fact a hyper network. The local policy is used by the agents to solve the task and execute in the environment. The input to this local policy is a action observation history, which is tau I of agent I. And we just input the action observation history into this local policy, and the output of this local policy is a local Q values. Q values means the expectation of rewards when you take an action under specific action observation history. And then, since we have more than one agents, we need a mixing network so that we can learn the global Q value, which is a expectation of joint actions for the agent teams. And we just learn these global Q values as a mixing or combination of the local Q values. And these Q values will be updated by a very typical classic reinforcement learning target called TD laws, which is short for temporal difference laws. This laws is the same as the one in DQ1, which is used to solve the Atari games. And this is not novel, but the focus of our work is on how can we learn some meaningful roles in this role distribution. Actually, the roles of the agents form a space of the roles, and we want this space to be well formed, so that we introduce two laws, which is in line with our targets we introduced before. So the first law is called Specialized Laws, and the second law is called the Identifiable Laws. And we use these two laws for role learning, and we hope that under the encouragement and the optimization of these two laws, the role will just take on some expected properties. So let's introduce how can we design these two laws. The first law is called Identifiable Laws. Maybe, as you know, the identifiable laws, as introduced before, is that we want the agents to have some similar behaviors if they have similar roles. In another word, we want the behaviors to be identified by the roles, so that we propose to maximize the mutual information between the role and the action observation history of the agent. By maximizing this objective, the random variable of roles and the random variable of action observation history will have many information of each other, so that if you are given the role, you will know the behavior, and if you are given the behavior, you will know the role of the agents. However, the mutual information involves an integral over a continuous space, since the role space and the action observation history space are always continuous. So it cannot be calculated directly. So to optimize this goal, we just derive a lower bound of this objective. And since for the sake of time, I'll just skip the mathematical details, but if you are interested, we can just go offline and have some discussion. This lower bound can be transmitted into a loss, and in fact, we just optimize these laws to enable the behaviors to be identifiable by the roles. And the second objective is that we want the roles to be specialized. So what is specialized? Intuitively, we want when we are seeing specialization, we mean that for any two agents, we want them to have similar roles, or they have quite different responsibilities. So there are totally two possibilities for these two agents. Either they will have similar roles, or they will have quite different subtasks or behaviors, or we can use the word responsibilities. But realizing this target is quite difficult, because for the first thing, we just don't know which agents will have similar roles because they are learning from scratch, and it is very unclear which agents will have similar roles during the process of the emergence. And this is the first point. And the second point is also very difficult, because the similarity between the behaviors cannot be straightforwardly defined. But we can solve this problem together. We can use our method is that we introduce a learnable dissimilarity model, which is called DeFi, and we propose to maximize the summation. This summation consists of two terms. The first term is the mutual information between the role of an agent and the behaviors of another agent. So mathematically, it can be modeled as a mutual information between the role of agent I and the behaviors or the action observation history of agent J. And the second term is Dissimilarity Model. The Dissimilarity Model is the output or the dissimilarity between the action observation history of agent I and agent J. So these two terms, they just represent the similarity and the dissimilarity measures between these two agents respectively. In the meantime, we seek to minimize the number of non-zero elements in the matrix of D values. So as you can see, when we we are simultaneously optimizing these two objectives, either the similarity or the dissimilarity will be maximized. And since we are constraining, we constrain the number of non-zero elements in the D matrix, the value of D is only very large when the value of I is very small. So that is in line with our target. For any two agents, whether either they are very similar or their responsibility are very dissimilar. So this is a optimization problem which can be modeled as this one. So we are just minimize the non-zero elements, number of non-zero elements in the D matrix, and we have a constraint with this. The summation of these two terms is larger than a predefined constant. This optimization problem can be transmitted into a lower bound, again, like in the case of identifiable laws. So in fact, we are just minimize this lower bound shown here to make the rows specialized. So this is our method. When just optimizing these two laws, which is identifiable laws and specialization laws, our method, which is the red lines, can significantly outperform some state-of-the-art multi-agent reinforcement learning algorithms. But that is not the focus of our paper. We are more interested in the row representations. So here we show some screenshot from StarCraft 2 games, and the first row is these snapshots, and in the second row we just show the corresponding row representations. For example, in the first time step of this game, this is a game in StarCraft 2, and there are 9 Marines, which is fighting against 10 enemies, which are also Marines. And here in the first column, we show the row representations and the game snapshot as the first time step. Here, the strategy is that the agents need to quickly form to set up an attack form, which is shown in the second column here, so that every agent can involve in the battle and they can fire at the enemies. And here we can see in the first at the first time step, the roles of the agent is characterized by their relative positions. For example, the agent to the red will have a very different role from the others. And the result is that they can quickly set up the attack form in the second column. Another example is at the 8th time steps, which is shown in the second column here. Here we can see that the roles of the agents is characterized by the relative by the hit points, which is the remaining health of these agents. We can see that the roles just change smoothly with the remaining hit points. The corresponding policy here is that the agents can alternating fears, which means that the agents with less hit points will just move far away from the enemies so that they will be protected. And after they're moving away from the enemies, they can just fear at a distance. In this way, the most injured agents are just protected, and the agents with more hit points will just take on more fears, and they together can deal more damage to the enemies. The similar phenomenon can be observed in some other time steps and also in other tasks. here we show the role representations at 3 different StarCraft 2 micromanagement tasks. We can always see some clustering or well-formed role space. And here we show the function of our second laws, which is the specialization laws. We can see that the dissimilarity model learned by our method is very meaningful. So the dissimilarity, the similarity between the agents with the same role is about 0.95, and the maximum value is 1. In contrast, the dissimilarity between agents with different roles is 0.07. And the figures here show the evidence study of the 2 losses. We can see that without the specialization laws, the performance will drop significantly, and the learning will not be very stable. And another very interesting observation is that we can see a very close connection between the emergence of the roles and the boosting of the team performance. For example, as shown in this figure, after 500,000 training steps, there is this clustering among the agents, but it is not very clear. It's some kind of weak, as shown in the second picture in the second row, and correspondingly, the team performance now is 0, which means that the agent cannot win a game here. But after this row clustering is formed, the team performance begin to increase. And after 4 million training time steps, we can see that there is a very clear row clustering among the agents. And as a result, the team performance has converged, and the agents can win nearly all the games in this reinforcement learning process. The same performance can also be observed in some heterogeneous teams. By heterogeneous means that in this task, we have different types of soldiers in the game of StarCraft 2. For example, here we show the results map which involves Marines, Medivac, and Maneuver. We can see that the roles of the agents is categorized by the type of soldiers in such kind of tasks. And there is also a very close connection between the emergence of roles and the increase of team performance. So that is our first work, which is called Roma. But the conclusion of Roma is that the concept roles has the potential to boost the performance of multi-agent reinforcement learning by encouraging the agent to take different subtasks. But it also have a very significant disadvantage, which is that we still need to search in the original action of the region space to encourage the emergence of roles. So in some very complex and real-world applications like sensor networks, we have thousands of agents. This work will not work efficiently. So in another work called Road, we proposed another method for learning roles. Our idea is that we can just decompose the action space first and learn the decomposition of observation of space accordingly. The idea is that in our human works, different subtasks often involve actions with different functionality. For example, in the game of football, we have some different actions like dribble and shoot and pass the ball, something like that. But different roles of agents will have different actions. For example, a goalkeeper, it never need to consider how to just shoot the ball and get a goal, right? So our insight is that we can use these properties of our human cooperation to just efficiently discover a set of roles. So we will first try to decompose the action space. And we want to model the functionality of the agents. The functionality of the agents can be modeled by the effect of these actions, which means that under action observation history, you take different actions and you will get different results. And the results can be modeled by the next observation, the next states, and the rewards you can take. So that we just train a forward model to learn the effects of the action. So here we just input the action observation history and the actions of other agents together with the action repetition of the action which we considered. So here we have an action encoder, and the input of this action encoder is the action which we want to learn the action repetition. The output of this action encoder is a repetition of this action, and then we can just concatenate the action repetition and the action, the observation and action of other agents into a forward model, and the forward model will just predict the next observation history and reward, and we can use the prediction laws and train this model. And the result is that we can get an action encoder which can just map the one hot action into a hidden space. So and we hope that in this hidden space, the actions can have some kind of clustering. For example, here in these tasks, the blue arrow means that the action can lead the agents to move forward to the enemies, and the red arrow will lead the agent to move far away from the enemies. And here we can see that after learning the effect-based action limitations, there is a very clear clustering of the actions. For example, the blue and the yellow point is, and the red point is very far away, but the actions which corresponding to move the agents neither forward or far away from the agents will cluster together. And some other actions like attack the zealots and attack the stalkers, these actions will just get close to each other and far away from the actions of the repetition of other actions. So that we know that if we learn some effect-based implementations, the actions will just cluster by their functionalities. And a similar phenomenon can be observed in some other tasks. For example, here the blue arrow and the red arrow is the moving direction of the ally agents. And the other actions are some attack actions. We can say that the move actions are far away from the attack actions. And in this way, we can get a space of implementations, and the actions will cluster by their functionalities, so that we can just run some basic clustering algorithms like k-means or x-means to just get the decomposed action space of this task. And then we just assign a role to each sub-action space. And in this way, we will get several roles. For example, in this example, we will have 3 roles. The first role is for move forward to the agents, and the second role is for moving away from the roles. And the third role is that the agents can attack the enemy units. And then the question is, how can we get the observation space of each role? To solve this problem, we just use a bi-level learning framework. Here shows a trajectory of the multi-agent teams. And from each state, we can get an observation. So here I will show the high-level learning algorithm, which aims at learning the role selector. So in this learning framework, the agent will first select a role by the role selector, and the team of agents will just take on this role and use the corresponding role policy to execute in the environment for several steps. And after these time steps, they will choose another role and use its action role reputation role policy to execute in the environment. So first, I will introduce the structure of the role selector. First, we will assign each role a representation. The representation of each role is just the average representation of the actions, as shown here. So the insight is that the roles are defined by the functionality of that of its action space, so that the average of representations can represent the roles with necessary information which we need to select the correct role for the agent to execute. So with this role representation enhanced, we just encode the local observation is another neural network and get a hidden representation of the observations. And then we just calculate the dot production between the role representations and the hidden representation of the observation. The result is some Q values of which we call rho I. The mathematical definition of rho I is the expected future return, which we can get if we select a role. And we will choose the role with the maximum expected return as the role in the future in the following several time steps. So here is a structure of the role selector. After selecting a role with a role selector, we will just use its role policy to execute in the environment. The question is, how can we learn such a role policy? Since this is a sequence and the agents have many previous observations and actions, we use a GRU to encode the previous experience of these agents. And the input to this action, to this encoder is the observation as its time step. And the HI here means the action and representation encoding from the previous time steps. And using the GRU, we will get a representation for the action observation history. And after getting these hidden representations, we will calculate the action, the Q values of the actions. Again, the Q values is the expected future return if we take a specific agent action. We just calculate the dot product between the action representations and the representation for the observation. And we will get the Q values of each action. And at each time step, we will select the actions with the maximum Q values for execution in the environment. And the Q values for the actions and for the roles will be trained by some classic reinforcement learning algorithms like Q-learnings. And we can just update this networks by propagating the TD laws of these reinforcement learning targets. And this is a learning framework of ROAD. The basic idea, again, is that we first decompose the action space, and we use the action information to decompose the observation space. In this way, we can just effectively get a set of roles. And here, one point I want to mention is that the action representation is pre-trained, but it will take very few training samples. So typically, the training will take 2 million steps for the policy learning, but the training for the action encoder and the action representations will typically take 15,000 of training samples. So by using this new method, we achieve the state of the art of multi-agent reinforcement learning algorithms on the StarCraft2 micromanagement benchmark. Here we show the results, and the y-axis shows the number of maps where each algorithm has the best performance. And here we can see that our algorithm, which is ROAD and shown by the red lines, it just outperforms in 10 out of 14 maps from this benchmark. And the outperformance of our algorithms is more significant in super hard maps. Here we show the 5 most difficult maps from this benchmark, and we can see that our performance with the red lines just outperform other algorithms by a large gap. Since we introduced the concept of roles and some specific special structures for learning role selector and role policies, a bonus of our method is that it can realize some kind of zero-shot policy transfer. For example, here we train on a source task, which is shown on the left. Here, 6 zeros is fighting against 24 ziglings. And we want to transfer the learned policies on this map to other unseen maps. Here we show the results. After trained on a map with 6 allies and 24 enemies, our method can be zero-shot transferred to many other maps. And for example, it can be transferred to a map with 18 allies and 36 enemies. There will be 3 times the number of agents in this map, and the agent team can still win in nearly a half of the games. This is a bonus, which means that the policy can be zero-shot transferred to a new task. This is my talk today, and I hope that the robustness or the security of multi-agent reinforcement learning, especially role-based reinforcement learning, is a concern of reinforcement learning community. Recently, I worked with Jingfeng and we studied the robustness of multi-agent reinforcement learning, but we haven't extended that work to the multi-agent cases. So I hope that in the future we can have more cooperation opportunities on the topic of robust and security of robustness and security of reinforcement learning. Okay, thank you. That is my talk today.
Thank you, Tonghan, for your great talk. It is indeed very impressive. Your work can achieve the state of art on 14 benchmarks. That is quite impressive. Basically, for my opinion, I have some question in general, kind of like we know that when the AI deployed in the real world situations, for example, the multi-agent reinforcement learning, we always care about the safety, the security. We know that there are many works on the robustness on reinforcement learning, but for the multi-agent reinforcement learning, the robustness is quite sparse. Can you share some perspective on the robustness in multi-agent reinforcement learning, kind of like security related things? What do you think about this?
Okay, sure.
Thank you.
My first opinion is that multi-agent reinforcement learning in real world is more sensitive, is more security sensitive when compared to single agent reinforcement learning, because many real world applications involves more than one agents, right? For example, in autonomous driving, you are not controlling one car, you are controlling many cars with, for example, going through a crossroad. Another very important application scenario of multi-agent reinforcement learning is human-computer interaction, which means that reinforcement learning agents is interacting with a human and they together solve a task. And for example, in some factories, you have human workers and you have robot workers, and you want them to just work together to solve a task. And in this case, the security of reinforcement learning is very important because you don't want the robot to hurt the humans. In these scenarios, it involves a multi-agent reinforcement learning than single-agent reinforcement learning. So although this application is very common in real world, the study of multi-agent reinforcement learning, as as mentioned by Jingfeng, is very sparse in the literature. The first reason is that multi-agent reinforcement learning is a very new field of research. I think the first paper on deep multi-agent reinforcement learning is published at about 5 years ago. And the main focus of researchers in this field is on how we can develop more efficient algorithms and which has more satisfying convergence property in some complex tasks. I think in the 5 years of multi-agent reinforcement learning research, the security is not a very central problem in this field. But nowadays, it is becoming more and more important because, as I know, some companies in China, they just use multi-agent reinforcement learning to develop autonomous driving cars. The robustness of multi-agent reinforcement learning is just becoming a very hot topic in this field. Since there are not many measures for the robustness of multi-agent reinforcement learning, that will be a good opportunity. However, there is a very big challenge in the realization of robust multi-agent reinforcement learning. That is the training setup in a typical multi-agent, capable reinforcement learning paradigm is the same to the test task. It is not trained to get to adapt to some expectations in the test time. So if we want to introduce some robustness into reinforcement learning algorithms, we need to just change the training setup, but that will violate the basics or the basic assumption of reinforcement learning. So that is the biggest challenge, which I think is in the multi-agent reinforcement learning paradigm.
Thank you very much. Thank you for your inspiring perspective, and we very appreciate your great talk today. Hopefully, when the situation lifted, we could sincerely welcome you in our Nihonbashi office in Tokyo. Okay. All right.
Thank you.
If there are no questions coming up, this is the end of our today's talk. Again, we very appreciate our speakers, Tonghan and Vikash, to give us 2 excellent talks. All right, that's all. Thank you very much. Bye-bye.
Bye-bye.